Okay, so we're
Okay,
very happy to have Elliot Cheung joining us from UBC, who will talk about discretization of Chern-Simons theory.
okay. Thanks, Francis, and thanks for giving me the opportunity to try to share about some of these things. This is basically work that's involved with my thesis, and I'm working on this with my advisor, Kai Behrendt. So the title is Towards the Discretization of Chern-Simons Theory. So I'll be kind of trying to give an overview of Chern-Simons theory and what that's all about. And the whole idea here is that we're using derived geometry to discretize Chern-Simons theory. So I'll explain a little bit about what that is the best I can. And then where derived geometry comes from in this context will be from L-infinity algebras. And these are just generalizations of Lie algebras and differential graded Lie algebras where Jacobi axiom holds up to homotopy, coherent homotopies. And then we'll get into the actual discretization process where we build a model in derived geometry that will be built out of finite dimensional pieces. And then we'll see what that has to do with Chern-Simons theory in the end if we get to there. Hopefully we will. So Chern-Simons theory itself probably means a lot of different things to different people, but to me, it's gives us a formalism for understanding the geometry of moduli spaces of bundles of flat connections up to gauge equivalence for a closed oriented three manifold K. We put MK for this moduli space, of flat connections up to gauge equivalence. So out of Chern-Simons theory, we'll see that one should be able to produce manifold invariants. And we'll talk about more of this later. However, the space of connections, flat or not, tends to be an infinite dimensional space. And this leads to complications when we try to produce invariants. Because for example, some techniques require taking integrals over infinite dimensional space. In fact, when people usually describe Chern-Simons theory and how it can be used to produce invariants, they often work with a toy model where the formalism is outlined in a finite dimensional setting. So using derived geometry and homotopies of derived spaces, we can relate Chern-Simons theory to a more finite dimensional setting and make these toy models into reality. I've put quotes by these words because they might not mean anything to you yet, but hopefully they will in a bit. So now let me give an overview of Chern-Simons theory. So we restrict our attention to describing connections on the trivial bundle over K. And since we're looking at connections on the trivial bundle, we can describe these as matrix one forms. Just one form is valued in n by n matrices. And gauge theory people will call these fields. On fields, we have this Chern-Simons action functional, this formula. So recall that K is a three manifold, so the thing inside is a three form. And this wedge product here is a combination of wedge product of differential forms and matrix product. And this bracket is just commutator bracket of that matrix wedge product. This action is gauge invariant up to integer multiple of 4 pi squared. This Chern-Simons functional enjoys this special property that its derivative at a connection A is given by this formula. And then here's the dependence on A over here. And recall that this equation, this part here equaling 0, is precisely the defining equation that expresses that A is a flat connection. But you may also recognize this as an example of a Mark-Katon equation for a differential graded Lie algebra. And indeed, it is the Mark-Katon equation for this differential graded Lie algebra of matrix forms with the de Rham differential and the commutator of the matrix wedge product. So if my connection is flat, then this term here will be 0. So then flat connections on K arise as solutions to a Mark-Katon equation, as well as being the critical set of a function. In particular here, the Chern-Simons action. So these important properties together govern a lot of the geometry behind flat connections on a 3-manifold. So now let me say a few words about how one might produce manifold invariants out of Chern-Simons theory. So significant insight due to Witten is how you might do such a thing. And you do this by taking the so-called Chern-Simons path integral. Here, dA is some sort of measure on the space of all fields. And recall that this is an infinite dimensional space. H bar is some sort of quantum parameter. And this will produce manifold invariants at particular values of H bar. Or you can think of this as a formal invariant given by a series in H bar. Although this sort of expression is mostly heuristic, as it's unclear how to define this measure over all fields. However, there are some ways that people have come to trying to understand what you should expect out of such an integral. And through something called the stationary phase approximation, we can kind of imagine what you can expect. In a finite dimensional setting, we can look at integrals that look like above, like these are just path integrals. You can call these path integrals in general. These are called oscillatory integrals, actually, I guess. You can look at these oscillatory integrals in the finite dimensional setting. For f, a smooth function, real valued function with non-degenerate isolated points. Then as h bar goes to 0, the stationary phase approximation gives you a series in h bar that's as an asymptotic expression of this integral. And it contains information about f at a critical point, terms involving like the Hessian at f and so on. And if you want to sort of imagine what's going on with this integral, this is a real valued function. So when I do e to the I f, this is like valued on the circle. And then as h bar goes to 0, this is going to fluctuate wildly around the circle. And then on average, everything's going to cancel out except for things at the critical points. So,
excuse me.
So, yes.
The h bar, is that Planck's constant?
For us, this is just a formal h bar. And
sure.
I guess when
oh, sorry, no,
use
that's okay. Homotopy, right?
Yeah.
Yeah, that's fine.
Well, it's supposed to like represent h bar. Like this is like distance to the classical theory or something. But you can like if you work out a non-perturbative path integral, you can evaluate this formal invariant at actual values. But for this talk, h bar will be a formal parameter.
Awesome.
So, however, more often than not, the critical points of f are not going to be isolated. So in the Chern-Simons context, this critical set is given by flat connections. So yeah, so you want to, yeah, okay. So path integration has two main questions, probably among others as well. But how can we understand the path integral in this in a degenerate setting? And how can we understand the path integral when the space of fields is infinite dimensional? So let us see how Batalon-Vilkovisky formalism addresses the first question of degenerate critical point setting. And to do that, let us first pretend that our space of fields is finite dimensional. So I'll explain a little bit about what this Batalon-Vilkovisky formalism is, BV formalism for short. This gives us a way to define path integrals when you have a possibly degenerate situation. And the key idea is to use derived geometry. And one of the main ideas in derived geometry is that you can take resolutions of spaces. And I will elaborate on what that means later. It's a little different from like resolving singularities, but it's related still. Right, so we want to take derived resolutions of these spaces that is compatible with comparing path integrals. In brief, this is done by replacing our space of fields with the derived space of fields. This is, you can kind of think of this as like a homological, like parallel to a homological resolution. The path integral gets replaced with this BV path integral, where we also have this L, which is a -1 shifted Lagrangian, but this is just jargon if you've never heard of that. So you can just think of this as some sort of derived constraint submanifold inside our derived space of fields. So the BV formalism gives us a framework for understanding what kind of integrands can be paired with these constraint manifolds to produce numbers. So there's this BV operator in the formalism, so that this integrand being annihilated by this operator is precisely this defining equation that says that this is a valid integrand. Some people call this the quantum master equation, this thing here. So to perform BV formalism for Chern-Simons, the idea is to extend your Chern-Simons action to this action on derived fields such that this master equation is satisfied. And then you can do the BV path integral. However, even with the BV path integral, you'd still need to make sense of the BV path integral, which if in the infinite dimensional context is still messy. So to get around that, we can harness the flexibility of derived geometry. So in derived geometry, spaces can be homotopic or weakly equivalent, while not being necessarily equivalent on the nose. So back up there, when I was talking about resolving crit F, there can be many choices of resolution, and the different choices are homotopic derived spaces. So when we choose a resolution, we can vary our choice up to homotopy. So to make sense of BV path integrals, we can hope to make choice of resolution that is finite dimensional or somehow built out of finite dimensional pieces. And that's what we do. That's what we've done in this project.
I have a question about
yes.
your derived spaces. Which category are these resolutions living in?
So I'll elaborate on that
Okay.
in the next few sections. So we have two main constructions in theorems. One is we've managed to build such a well-behaved resolution of this gauge group quotient. And it is an simplicial derived space that's a limit of finite dimensional derived spaces. And then we can actualize the promises of BV formalism and produce this formal three-manifold invariant using this resolution we've built. So that's the context of the rest of the talk. So now let me address that question you just had and try to say something about derived geometry and how L-infinity algebras enter into the picture. So you can think of choosing a model of derived geometry by choosing some sort of embedding of categories from spaces into derived spaces, where this category derived spaces is some sort of category with some notion of homotopy. And what kind of category you might want that to be might include all these different kinds. There's an infinity category or model category, category with equivalences, so on, with varying levels of structure. So with the category of weak equivalences, maybe you only can talk about homotopies, but with infinity categories, you can talk about vibrant objects and make sense of taking resolutions of objects instead of just homotopies. Then if you have this embedding of spaces into derived spaces, there's this adjoint, which is called the classical truncation functor. So that if you ever mapped a derived space to a classical space, then it would have to pass through the classical truncation. So that's the universal property that it would satisfy. So this is just a general framework for how to do derived geometry, and a lot of it sounds like it's quite flexible, and it can be. In this work, we choose a model for derived spaces that they're called L-infinity spaces. And I'll explain what that is. So these are not as general as possible, but not as general as you can make it, but it's a more geometric model of derived geometry, perhaps. So here's how this works. So suppose that M is some sort of space, and it can be a manifold or an analytic space or algebraic variety scheme, as long as we have some kind of vector bundles on it. But pick whatever you want. So suppose that we have a strictly positively graded bundle on it, along with a section that goes to the first bundle, E1. Now this graded bundle, we can give the graded bundle the structure of a curved differential graded Lie algebra by just introducing these operations, like a bracket, a D, and a curvature. And its axioms just are word for word lifted out of how you would define a differential graded Lie algebra over complex numbers. It's just now everything is relative to M. So in particular, like this bracket satisfies a graded Jacobi axiom. But this D squared isn't necessarily going to be zero, but it's going to be zero up to this curvature term, bracketing the curvature term. So if this operation D squared over the vanishing locus of the curvature section will actually be zero. So you can think of this as the fibers of this bundle are curved differential graded Lie algebras over complex numbers, and then the fibers over the vanishing locus of the curvature section are uncurved differential graded Lie algebras. And you can generalize this above, so you can have the bundle can have a curved L infinity structure, which just requires you to include more operations that express that the Jacobi axiom is satisfied up to strong homotopy. So it's Jacobi holds up to homotopy, and you provide all the homotopies. So this tuple together, the manifold with the bundle over it, and the operations on the bundle, this is called an L infinity space. And this paper by Baron, Liao, and Zhu show that these actually do form a category of fibrant objects. So as long as you can embed your space into this sort of thing, you can take a resolution in this context. The classical truncation of an L infinity space is the vanishing locus of the curvature section. And I will make a remark here that it's important that these bundles are strictly positive in grading but yeah, strictly positive in grading. Otherwise, the classical truncation may look different from spaces. You can get algebroids instead. So it is something that people do, but in this case, we will not do that. So all our bundles have to be strictly positive in grading. So now, an important construction that I want to discuss now is how to produce an L infinity space out of an L infinity algebra. So suppose that L is a positively graded L infinity algebra, and we want to make a condition that there's some open neighborhood of the origin where this Markotan function converges. So usually the Markotan equation involves just these two terms, but in the presence of higher operations, it is a series, infinite series, involving all the operations. So there's a question of convergence of this function. But we assume that these L infinity algebras have a condition where we can find an open set where this converges. And now for the parts of the L infinity algebra that start in degree 2 and up, we take the trivial bundle over this open set. And then if we can twist the L infinity operations to make new operations by this formula. I forgot a 1 over k factorial here. And these give new L infinity, curved L infinity algebra structure on L. And it's curved precisely when X is not Markotan, and it's uncurved when X is Markotan, what you twist by it. So then we can package all these together to give bundle operations. And that's just over X. We take the twisted operation by X. So precisely what this L infinity space is saying that you have this open set U, and if you pick a different point, the L infinity algebra that is being parametrized here is L twisted by X. And the operations are defined by like that. Then we take the Markotan function, and that gives us the section from U to the first of these bundles, which is the second bundle. Everything. So this bundle starts in degree 2. Well, we shift the grading. Okay, never mind. Okay. So diagrammically, it kind of looks like this. And then, so this is the differential that's possibly curved. And there's some other operations, lambda n, that make this into a curved L infinity algebra in bundles. So this triple U script L starting from 2 and the lambdas give us an L infinity space, and we call this SLU, and it's supported over this open set. So this SLU may depend on this choice of open set, and if we take its classical truncation, what we get is Markoton elements that live on this open set. Markoton elements of the original L infinity algebra L that are on this open set. So we have some sort of functor that go from L infinity algebras that have this convergence condition and L infinity spaces, where you must choose some sort of open set. Under this functor, if I have homotopic L infinity algebras, then there are choices of open sets U alpha and L1 alpha and U beta, so that these are homotopic L infinity spaces. So I haven't quite explained what it means to be a homotopic L infinity space, but I did advertise to you that a derived geometry category has such a notion. And L infinity algebras can also be homotopic. So these are, remember, these are Lie algebras up to homotopy. So this is sort of like a homotopy respecting functor, at least locally. So this is that's kind of the framework that we work with, and now I'll explain how this is related to the Chern-Simons theory context. Let's go back to Chern-Simons theory. And recall that on a 3-manifold, these Markoton flat connections correspond to Markoton solutions to this differential graded Lie algebra, which is matrix differential forms. And this is a differential graded Lie algebra. In particular, it's an L infinity algebra. So we can take this corresponding L infinity space, and we don't even have to pick an open set U because there's only finitely many operations. So the Markoton function is just, got 2 terms, but it's supported over this infinite dimensional space.
Sorry, Elliot, just on that
Yeah.
point of the choice of that neighborhood U, that was just for the
Mhm.
convergence issue, right?
Yes.
Okay,
Yeah.
so in this case, because convergence is guaranteed, we don't need to worry about a
Exactly.
neighborhood U.
Exactly. In fact, you can take the bundle to be defined over the entire L1.
Okay, fantastic. Thank you.
Yeah. So now the game plan here is that we want to find a homotopic model of this differential graded Lie algebra that's better behaved. So the hope is then the corresponding L infinity space is also better behaved. And we do this by passing to a triangulation. So here we replace K with the triangulation of K. We can think of this now as a simplicial complex. Unfortunately, closed orientable 3-manifolds can be triangulated in a combinatorially unique way. In other words, different triangulations can be refined to each other by some chain of subdivisions. So on a simplicial complex, K, we can form simplicial differential forms. And for now, we'll talk about just the de Rham, like this C infinity forms without matrix coefficients. And we think of these as piecewise smooth forms on K with some regularity. So if I have a form on a P simplex, this comes from the restriction of a smooth form of some open set containing that P simplex. Then to specify a P form on K, we need to give a P form on each simplex, sigma and K, such that this collection of forms is compatible with intersecting on the faces and so on. So now, inside simplicial differential forms, we can pick out a finite dimensional subcomplex called Whitney forms. And as a chain complex, this will be isomorphic to simplicial cochains. And I'll explain how this works. By the way, if you've never seen this before, like by no means this original work. This is something that people have done for a while. I mean, Whitney did this. For each P simplex, sigma inside K, we can consider constant forms on it. We can consider the top volume forms. This integrated over sigma is 1. And we would like to extend this to a smooth form on this whole simplicial complex. And we want to extend this by saying that restricted to sigma itself, it should be that volume form, and restricted to other faces, P faces, I should get 0. Now, Whitney forms precisely solve this interpolation problem. In other words, a Whitney form constructs such a smooth form that does this. And if I want my interpolated smooth form to be linear, then this is a unique solution. So first we'll say, suppose that K is an n simplex, and I have a sub P simplex in K. You define this Whitney form associated to this face by this formula here. And there are some global coordinates on K that satisfy this. That's what these coordinates are. These coordinates are picked out of the global coordinates. So let me illustrate this with an example. I pre-wrote this to save some time. So suppose K is the 2 simplex. So I've got these coordinates, T0, T1, T2. And then I look at the Whitney form associated to the 0, 1 edge. So this is, in the end, this is supposed to give me a 1 form. And what I want it to do is on the 0, 1 edge, it's this volume form. And on the other edges, it's 0. And then it should be a smooth form inside. So just by inspection, we can see that if you pass to the restrict to the other 2 edges, 0, 2 and 1, 2, it's 0, right? Like, yeah. So this edge leaves out the T0 coordinate. So this thing is 0, and then this thing will also be 0, and so on. Now, if we set T2 to be 0, we're on the 0, 1 edge. And then the global coordinates act like this, T0 plus T1 plus T2 is 0. Then you make this substitution at T0 is T1 minus T1 minus T0 is T1 minus T1. And then you work this out, and then these cancel, and you end up getting DT1. So it's constant 1 form on the 0, 1 edge. and it integrates on the 0, 1 edge to give you 1. So then that means you see that this expression does the required interpolation. Okay, so that's what Whitney forms are. So then, well, Whitney forms, so those are Whitney forms, Whitney elementary forms. So that's a Whitney form associated to a specific face. So in general, we take the vector space generated by these. And then for a general simplicial complex that isn't just delta n, you can perform this construction locally on each piece and on each simplex of K. So it's going to be a direct sum of all the Whitney forms on each simplex. You can check that for a Whitney form associated to a face sigma, its de Rham differential gives you a Whitney form associated to the boundary of that face. So you can identify Whitney forms as a copy of the simplicial cochain complex. And you have this chain map going from the cochains to differential forms. So just remember that cochains is just, if you take a face, you can evaluate a number, and these Whitney forms are essentially just constant differential form on a given face, and then it's uniquely extended to an interpolated form. So there's also this projection map that's easy to describe. You just, if you're given a differential form, you just sum over all the Whitney forms associated to the faces, and you take just the integral of that form over that face. Now these two maps I, W, and P, rho, W together actually packages to a deformation retract of these chain complexes and this chain homotopy. So then, in other words, this is identity going this way, but this way is not identity, but it's chain homotopic to the identity via the Dupont homotopy operator. Now, as you may know, if you have isomorphic vector spaces and you define some sort of algebraic structure on these vector spaces, then you can pass them to each other by way of this isomorphism. Now, what this situation is that we have two homotopy chain complexes, and on this side, we have the structure of a DGLA. So what happens under deformation retracts is that we get a homotopy version of the structure on the right onto the contracted complex, and that's an L infinity structure. So that means the Whitney forms now get an L infinity algebra structure. So, but we do this with matrix coefficients, which you can carry this out with matrix coefficients. So now we have a differential graded Lie algebra omega k GLN and an L infinity algebra Whitney forms over K with matrix coefficients. And there's inclusion, L infinity morphism that goes like this. And this L infinity morphism, this inclusion is a homotopy. So remember this L infinity algebra is supposed to be a deformation retract of this differential graded Lie algebra.
Sorry, Elliot.
Yes, yeah.
This homotopy transfer argument is certainly a clean way to see how we get an L affinity structure on those Whitney forms, but does it
Yes.
give us more mileage in terms of writing out explicitly the higher L operators?
Yes. Oh,
Oh,
yeah.
it does.
No, totally, yeah.
Oh,
So
great.
yeah,
Great,
you can.
thanks.
There's some trees, some formulas that you can. So, for example, like you can write the bracket on Whitney forms as like here's the homotopy and here's inclusion and here's the bracket upstairs. So then the L2 of XY is like homotopy of the bracket of X, Y, like this. So that there's a way to like
yeah.
write
Right,
down
actually,
all these trees to do it. Yeah.
right, and that formula works really for any transferred L infinity structure of that form, transferred from a DGLA, right?
Yeah.
Okay,
Yeah. So in
great.
fact, like this thing is just like a M2, like similar formulas for A infinity and so on.
Right. So in this case, we can use those formulas and write down the L infinity structure on Whitney forms.
Yes. But you may have to write down a lot of terms, but it can be
Right.
done.
All right, thank you.
Right. So okay, so we have this L infinity algebra. That's the deformation retract of this differential graded Lie algebra. Right. So now we would like to make this claim that we can find these open sets so that these corresponding L infinity spaces are homotopic. But note this sleight of hand here, where now we restrict these gradings to be strictly positive. However, we need the whole complex to form homotopically infinity algebras. We can't just chop off the degree 0 part and get homotopic L infinity algebras. Although if we chop off, of course, this inclusion, this map is still an inclusion even if we chop off the degree 0 part, but it's not going to be a retract. And essentially the difference is if we're allowed to chop off the degree 0 part or not, that means if we're not allowed to just chop off the degree 0 part, that means morally speaking, the corresponding L infinity spaces are only homotopic up to gauge equivalence. So we need to account for gauge equivalence here. So to understand gauge equivalence or flat connections, we have to resolve this flat connections mod gauge quotient in 2 steps. First, we take this resolution of this quotient and represent this as a simplicial space or scheme in the usual way, like this. So this is an action groupoid. And then, after resolving this quotient to a simplicial space, we'd like to apply derived resolutions at each simplicial level. Turns out that we can do this by first we take this simplicial differential graded Lie algebra. This is cochains on delta n valued in omega. And diagrammically looks like this. So see, the thing is, note that since we're introducing cochain degrees, when we look at something like this, and when we work with L infinity spaces, we always require that our algebras are strictly positive in grading. So we stick a greater than or equal to 1 here, but that's total degree. So now that we've introduced cochain degrees, we can actually start to see the degree 0 parts pop up in components, cochain components that are greater than 0. So in degree 0, it's just the matrix forms. And then when we resolve this, we can start seeing the gauge part come in. Now we can take this Whitney inclusion map on each simplicial level. So the Whitney version of this cochain algebra looks like this. Just Whitney forms instead of differential forms. And then we take the L infinity space functor at each level and get this simplicial L infinity space where you've picked suitable open sets. So now if we take the classical truncation of this thing, we actually do get the gauge groupoid restricted to sufficiently small flat connections, accounting for this open set that we have to pick. So this is some sort of local derived resolution of the original quotient. Oh shoot, sorry. So to globalize this, we pass to subdivisions of the triangulation. So if you take a subdivision of the triangulation, you can include simplicial differential forms, right? Because if you're piecewise smooth with respect to the subdivided complex, then you're indeed, oh sorry, if you're piecewise smooth with respect to K, then you're indeed piecewise smooth with respect to the subdivided one. And this subdivision induces L infinity morphism on this corresponding Whitney forms. And then if you run the thing upstairs and produce these local L infinity spaces, we can string them all together in this diagram, passing the subdivisions, iterated subdivisions. Now this diagram can be endowed with strong homotopy data for a homotopy inductive limit. Explicitly, that means you can look at length n paths in this diagram and all their concatenations. So we can explicitly provide homotopies between all these length n paths and their concatenations. So you put this ex w for this diagram with all its homotopy coherence data. This thing represents the ho-colim of this diagram. So in the end, the kicker is that this ex w is a limit of finite dimensional L infinity spaces, in the sense that all the L infinity spaces that show up in the diagram are finite dimensional, and this thing is the limit of these things. So it's an infinite dimensional simplicial L infinity space, and the big one of the theorems that we prove is that this actually covers the moduli space, global covering of the moduli space. So we take its classical truncation, it does indeed recover the moduli space. So put differently, that means we can prove that for any connection, you can sufficiently subdivide K so that A, the connection is gauge equivalent to an element in this Whitney inclusion map, the image of the Whitney inclusion map. So it's gauge equivalent to some Whitney form, L infinity Whitney form. Okay, so that's this ex W sort of like the main construction that will set everything off, and that now we have this morally finite dimensional model of the Chern-Simons moduli space. We can try to work with it and see if we can produce invariants and understand its geometry and so on. So indeed, we can pull back the Chern-Simons functional to this Whitney model and get, because I mean, explicitly just recall that the Chern-Simons action is some sort of functional on matrix forms. So, and W1, like W1 lives in maps in here, so you can just pull this back. So you can do that at every refinement and piece them together and get this homotopy Chern-Simons functional in the limit. So now we can construct this BV operator and this BV extension of the action so that this quantum master equation is satisfied. So that's one of the big theorems that we can prove. And if you know anything about derived symplectic geometry, this EX W is supposed to be a homotopic model for the derived moduli space of flat connections and for a 3-manifold, and that's supposed to have a symplectic -1 shift to symplectic form, and this does. And the content of this theorem is that you can pre-quantize this symplectic form in this derived sense. And this is equivalent statement. So now, after you've done such a thing, you can try to carry out the promises of BV formalism and produce this global, well-defined Chern-Simons path integral in this homotopic model and produce 3-manifold invariants. And this is supposed to have, this whole thing is also supposed to have interesting relations to Casson invariants as well. So that's kind of like the punchline. Okay, so that's it. Thank you for your attention and listening to my talk.
Great. Thank you.
Any questions? Or you're supposed to ask that?
Yeah, I guess, does anyone have any questions?
I do have a question.
Sure.
Can you go back a few slides to your sequence of simplicial L infinity spaces?
This thing here.
Yeah, exactly. So just to clarify what's going on here, you're saying that we have a map from one simplicial L infinity space to the next, just induced by subdivision. And we also have longer maps comparing the different spots that are a few steps apart, but it's not, it doesn't commute on the nose, but it is
exactly.
it's homotopy commuted. Is that an example of the what do they call it? Infinity commutative diagrams in the sense of Dwyer, Kahn, Stover in the 80s, right? That stuff?
Okay.
Okay,
So
you have...
if you kind of do this arrow here is defined by, well, so the thing is, like, I've only kind of included the one-step subdivision arrows, but you can also go like take like the second subdivision like this, right, straight on.
Right, you have those. They're there by
yeah.
construction.
Yeah. So that's also baked in there. So that's kind of like sigma 2 maybe. So then you can also do a one-step subdivision like this. And then the corresponding L infinity spaces here, there you can explicitly build this homotopy between them.
I see. But yeah, in that older work from the 80s, the question was when can you strictify just a homotopy commutative diagram to a strict diagram? Here, that's not the issue. All you want is just have enough data to compute the homotopy colimit of that sequence, right?
Yeah.
Okay.
Yeah. So I guess Yeah. So I think, well, the thing is, if you have like a sufficiently nice category that these L infinity spaces assemble to, you can just draw this diagram and be like ho-colim and call it a day.
Yeah.
But it's not necessarily very explicit. You know, you might have to pass the zigzags and stuff, but here, like, you actually give all the homotopy data.
Right,
so
that gives you a recipe really, for the homotopy colimit.
Yeah, exactly. So you really don't have to say you never have to say ho-colim if you don't want to.
Got it. Thank you.
Yeah. Thanks. Thank you.
I have a question. Can you go to the slide
Yeah.
before?
Before this?
Yeah. Oh, before that a little. Yeah, the one where you have the picture.
This one?
Yeah. Yeah. So for example, on the one where you have the ones simplices, you have like the omega 0 on the edge.
Mm-hmm. Mm-hmm.
So there you would just have matrix valued functions.
Yeah.
But for the gauge group, they should be invertible.
Oh
So
yeah,
how?
yeah. So yeah. So I kind of excluded that, but the point is that if you take the invertible, this actually is a subtle thing. But if you take the units of this, this is like big GLN that. So if you take invertible coefficients, matrix coefficients, that is just coefficients valued in invertible matrices. So that means there's a big open set, and there's an open set in here that where the invertible gauge action transformations live.
So
So you
is
have
that,
to do everything with respect to this open set.
I see. But when you take the open set, like for the Whitney forms, you take a
But
little.
sorry, go on.
It's going to be an open set around the identity or something. So as long as you take a small enough open set, it's enough. Is that the idea?
Right. So okay. So first of all, here, recall that these edges where you have like omega 1, omega 1, omega 0, like this is the degree 1 piece of this thing here. So the open set in here in the degree 1 piece is going to be intersected with the open set that makes this thing invertible.
So it's something you have to add in by hand.
Yeah, but remember, like we're allowed to pass to open sets in the degree 1 piece anyway. So
Right.
you're not taking an open set in like the higher coordinates.
Right.
And yeah, so that's what's going on there. And there is a subtlety about how the Whitney form of this diagram represents the same thing, because it doesn't, like, these are not actually equivalent on the nose. You do have to pass to the subdivisions.
Right.
Yeah.
I see.
But this is still an L infinity morphism that is an inclusion that goes one way. So everything kind of cleans itself up when you pass to the subdivision limit.
Okay, makes sense.
Yeah.
Are there any other questions? Okay, if not, let's thank Elliot again.
Okay. Thanks for listening.
Thank you.
Okay.